So constrained optimization problems happen all over the place. When I say Gibbs free energy minimization, I'm thinking about the context where, like, okay, I've got a reaction, a chemical reaction. I know it's going to equilibrium. We're giving it sufficient time and sufficient temperature that this reaction is going to go to equilibrium. And what are the constraints in a chemical reaction? Well, there's a heat balance, right? You can't create or destroy chemical energy. It's either stored as chemical potential in the bonds or it's stored as heat in the temperature of the material. And so you've got that balance there. You also have like the material balance of every atom, because if it's just a chemical reaction, then the number of atoms of every element are going to be the same. And so you have these certain constraint equations, and what you're trying to do when you calculate the equilibrium state of a chemical system after a reaction is you're trying to minimize a quantity in thermodynamics called the Gibbs free energy. And so you specify a function that will give you Gibbs free energy as a function of all of the chemical concentrations and temperatures and pressures. And then you specify what those constraint equations are, and it gives you a math problem. Constraint optimization also happens in manufacturing, logistics, doing best fits of math models to empirical data, which happens a lot. So one method that we can use to solve constrained optimization problems is called the method of Lagrange multipliers. So we want to find either the maximum or a minimum. That's what we mean by optimization, is we're finding the maximum or a minimum of a function. And we've got a system of constraint equations. First, step one, define what we call the Lagrange function. And that's usually a stylized capital L. And that's going to be equal to the function I'm trying to optimize plus the sum of all of the left-hand sides of those constraint equations, where you set the right-hand side equal to 0, the left-hand side is everything else. Add all of those up. And the other thing here, that little lowercase lambda, is called a Lagrange multiplier. After I've defined what this Lagrange function is, we find the critical points. That means you take the gradient of the Lagrange function, set it equal to the 0 vector, and make sure that every entry in the gradient of the Lagrange function is set equal to 0. You're going to end up with a system of equations, and you just got to solve that system of equations to get the coordinates of all the stationary points, right? And then after I have the coordinates of the stationary points, we know that every stationary point could be a maximum, could be a minimum, could be neither. Normally in this context, you are just going to rely on your knowledge of the problem. I'm not going to give you any like real-world examples today, but in practice, if I was using the method of Lagrange multipliers to optimize a function, it depends on what function I'm trying to optimize. Like if I'm trying to minimize Gibbs free energy, there's going to be one stationary point, and that's going to be the minimum of Gibbs free energy. I don't have to wonder about whether that's a maximum or a minimum or neither. If I'm doing something with like manufacturing, then I want to optimize profit. It's probably likely that the only stationary point is going to be a maximum for profit. And there's 1,000 different ways that you can decrease your profit, but there's only one optimal way. And so you expect the only stationary point to be a maximum. And that's what I mean by you must rely on your knowledge. Not only is that easier, but also the second derivative test that we talked about last time, where you take a function of two variables, and then you take the second derivatives, second partial derivatives, and you do blah, blah, blah to it. That's not going to work in the context of Lagrange multipliers. Number one, because we are going to have more than two variables. And so then you might say, well, okay, last time we only talked about the second derivative test for 2 variables, but what if I have, the second derivative test for 5 variables, where we take the Hessian matrix and we take the eigenvalues and we look at the eigenvalues of the 5 eigenvalues. We look to see if they're all positive or all negative. The problem is that with Lagrange multipliers, the Lagrange multipliers could be positive or negative, or their second derivatives can be positive or negative, and it doesn't really matter. So the second derivative test can sometimes, in this case, tell you have a saddle point. When you don't have a saddle point, you actually have a maximum or a minimum. I have this bad habit of talking too much. All you really need to know is on the screen. So if I'm starting to ramble and you feel like I lost you there, like with the eigenvalues and everything, forget about that, okay? All you really need to know is this stuff. Define the Lagrange function, find the critical points. Okay, let's do an example. Or maybe not. But before we do an example, let me try to explain why this works. Because hopefully, to all of you good math students out there, you're thinking, okay, that sounds a little bit crazy. Why would I define the Lagrange function that way? And then why would the critical points of the Lagrange function have anything to do with this constrained optimization? So this is what we're going to do for this example. I've got a function, and that is x squared minus y squared. And if there were no constraints, well then the range of this function goes from negative infinity to positive infinity. And so if I don't place any constraints on this domain, well, then there's not a maximum, there's not a minimum. I can always find a point on this function that gets me a larger value, and I can always find a point on this function that gets me a smaller value. This is only an interesting optimization problem if I supply some kind of constraint equation. And so if I obey this constraint, it's really going to restrict the domain that I'm working with. This is an ellipse in the xy plane. And so instead of my domain being all real numbers x and y, instead of my domain being the whole xy plane, what I'm saying is, let's just restrict my domain to this set. And out of those x and y coordinate pairs that lay on this ellipse, which one of those is going to give me the maximum value of my function, and which one of those points is going to give me the minimum value of my function? That's what I mean by, let's find the max and min of f subject to this constraint. It means only look at those points in the domain and figure out which one's the max and the min. So let's cross our fingers and hope that this link works. Please, GeoGebra. Please. Opening file failed. Thank you. Thank you so much, GeoGebra, for doing what you always do. Maybe if I sign in first, it could help. I don't know what my password is. All right, so we're going to do this the old-fashioned way. We're going to say x squared minus y squared. And then we're going to say 2x minus 2 squared plus, what in the world? This is unacceptable. Like, it's such a bad website. I know this would never happen in any world, but I really wish some GeoGebra software developer one day watches one of my videos and fully appreciates what they've done. Y minus 1.1. Okay, I'll just have to start a new line.
You should label the video like, this is why GeoGebra sucks. 3.5 minutes.
Okay, so we're almost there. Okay. So the function that I want to optimize is in red. And like I promised, you can go up to infinity or down to negative infinity on the red surface. But we said, okay, let's only allow the values of x and y that fit on that ellipse, right? So the intersection between this, teal elliptical cylinder and the surface are the only values I'm considering. And I can even make this look a little bit more. Select two surfaces, 1, 2. Let me try again. 1, 1, 2.
I can hear them.
Okay. Okay. So I can't highlight it for you, but look, that's the point we're looking for. Do you see the intersection between the red surface and the blue elliptical cylinder? That's the maximum of my function subject to the constraint. Okay. And then the minimum of my function subject to the constraint would be there. At that point. Okay. All right. The next thing I want to show you is almost definitely going to be easier than that. In green, I've got a topographical map of that function, right? You saw the hyperbolic paraboloid, the red surface on GeoGebra. Well, now in green, I've got a bunch of different level sets of the same function. So, this is where it's like, pretty low, and this is where it's pretty high, and it's increasing as you cross the level sets. And in purple, I've got the same ellipse in the xy plane that tells me what's the domain I actually care about maximizing this function on. And what I want you to notice is that when I set my function value equal to a constant, that creates a level set like you see in green. When I set my constraint equation on there, typing out something like 2x minus 2 squared plus y minus 1.1 squared minus 1 equals 0, that is also a level set of a function, right? If I say, let's say this part is the function g, the left side of the equation is the function g, then setting it equal to 0 means I'm talking about a level set of g. Then this is the maybe crucial part here. At the maximum and minimum points of my function, along the level set where g is equal to 0, these level sets are tangent to each other. So here's what I mean. I've got an adjustable part of my level sets right here. This one I can tweak to make the function value at the level set whatever I want, okay? So whenever I have this level set of my function intersect and is tangent to the purple curve, that is going to be the maximum of my function subject to the purple constraint. Because if I choose a larger value of my function, well, then there's no values in the purple domain that can get up to that value. And if I choose a smaller value of my function, well then yeah, there's points on the purple domain that attain that function value, but there's also points that could have gotten a higher function value. So you choose exactly the function value that barely touches the purple domain at one point, and they should be parallel to each other. They should be tangent curves to one another. And then likewise, if I go over here and I find the minimum value of my function with respect to this level set, I can tweak the minimum value, and here's values that are lower than the minimum and values that are higher than the minimum. And if I really tune it in so I get exactly the minimum value of my function on this purple domain, then there's only one point, and it's the point where these level sets are tangent to each other. They intersect at one point and they have the same slope, the same direction. Okay. So that's what I'm saying here in the third bullet point. At points where these two level sets are tangent to each other, they have parallel orthogonal vectors. So if I have this purple set, and then I have this green set, and they happen to be tangent to each other right here, well, the orthogonal vector of the purple set is going to be parallel to the orthogonal vector of the green set. Since the level sets are kind of moving in the same direction alongside one another, then any direction orthogonal to that direction is the same. So that's the fourth bullet point. We learned last week that the gradient of G is orthogonal to all of the level sets of G, and the gradient of F is orthogonal to all of the level sets of F. That means the gradient of G must be parallel to the gradient of F. So those two gradient vectors are equal to each other up to a constant multiplier, a scalar multiplier. So k is a scalar. That's what it means to have parallel vectors. And then lastly, when I say we are going to define this Lagrange function as being f plus a scalar times g, and then I take the gradient of the Lagrange function, and then I take the critical points of my Lagrange function, I'm setting the gradient of f plus lambda times the gradient of g and setting that equal to 0. In other words, I'm saying that gradient of f is equal to negative lambda gradient of g. That means we are requiring that the gradient of g has to be parallel to the gradient of f by taking the stationary points of the Lagrange function. And I'm forgetting one thing, actually. What I'm forgetting is this. Is that if my function f is a function of x and y? Then my Lagrange function is going to be a function of x, y, and lambda. So really, when I talk about the gradient of the Lagrange function, I'm talking about a three-dimensional vector. One is the partial of the Lagrange function with respect to x. The next entry is the partial of the Lagrange function with respect to y. And the third is the partial of the Lagrange function with respect to lambda. And so what I wrote down right here is not 100% true. What I should have written for the gradient of lambda times g is maybe something that looks more like the derivative product rule, which is like the derivative of lambda times g plus lambda times the derivative of g. There we go, derivative product rule. Of course, but we just said that we're making sure that g is equal to 0, right? And so this part goes away and is 0. And again, when I take the gradient of the Lagrange function, forget the first two entries for right now. Focus on the third. What is the partial derivative of my Lagrange function with respect to this lambda? Well, there's no lambdas here in the first term, right? So the partial derivative would just be 0. And then over here, I've got lambda times a function that has nothing to do with lambda. So when I take the partial with respect to lambda, this is basically a constant. G is a constant. Then when I take the partial derivative of lambda with respect to lambda, it's just 1. And so whenever I do this, and you'll notice this more when we start working some examples here in a minute, that third entry in my gradient of the Lagrange function vector is just going to be the g function. And so later, whenever I go to take this gradient of the Lagrange function and I set it equal to 0 so that I can find the stationary points, one of those equations, the equation at the very end, is setting my g function equal to 0, which means that I'm actually having to enforce this idea that the g function is going to be equal to 0. I'm going to respect my constraint at the stationary points of the Lagrange function. Sorry. That was very verbose. It's a very verbose way of saying if I make the stationary points of the Lagrange function, then I've made sure their constraint is respected and the gradient of g is parallel to the gradient of f. And that should work based on the sort of geometric pictures of the level sets and the constraint. Anyways, let's do some examples. Find the minimum and maximum of this function, x plus 2y plus 1, with respect to the constraint and this is an ellipse, but got a nice linear function and then an elliptical constraint. So I rewrite the constraint so that the right-hand side is 0. And then this is my function g on the left side of that constraint equation. So when I go to write the Lagrange function, which is a function of x and y and lambda, this is going to be f plus lambda g, which is going to be x plus 2y plus 1 plus lambda times x squared over 9 plus y squared over 16 minus 1. So now let's take the gradient of the Lagrange function. And the first entry in my gradient is the partial of the Lagrange with respect to x. And that's going to be guinea pig. Yeah. That's going to be 1 plus there you go. The next entry in my gradient of the Lagrange function is going to be the partial of L with respect to y. What is that?
2 plus
2 over 16.
And then the third entry down here will be the partial of the Lagrange function with respect to lambda. And what is that?
x squared.
So that's what I was trying to say earlier in abstract terms, is that like one entry in the gradient of the Lagrange function is always just going to be the g function. And so whenever I take now the stationary points of the Lagrange function, which are places where the gradient is equal to the 0 vector, we are going to enforce the idea that the g has to be equal to 0, which is then going to just enforce the constraint equation and make that have to be true. So I get a system of equations. My system of equations looks like 1 plus 2/9 lambda x is equal to 0. And the second equation is 2 plus 1 over 8 lambda y is equal to 0. And my third equation here is x squared over 9 plus y squared over 16 minus 1 is equal to 0. And with a system of 3 equations and 3 unknowns, there's a lot of different ways you can solve this thing. Like one thing I can do is take the first equation and solve for x. So I'll subtract 1 from both sides. Multiply both sides by 9 over 2. And then divide both sides by lambda. And then I could take this equation and solve for y. Subtract 2 from both sides. Multiply both sides by 8. Divide both sides by lambda. And then I could substitute these definitions for x and y into the third equation. And so I'll get something like negative, well, I guess when I square the negative, it makes it positive, so I don't really need the minus sign. But 9 squared divided by 2 squared divided by 9 is really 9 over 4 And then I need a lambda squared in there, plus y squared over 16. So that's 16 squared divided by 16, which should just be 16. I got to divide by lambda squared again. Minus 1 is equal to 0. Let me add 1 to both sides and multiply both sides by lambda squared. And so lambda is going to be the square root of 9/4 plus 16. 16 is 64/4, so that's 73/4, I think. Okay, and now that I know the lambda, I can go back to x and say, well, x is negative 9 over 2 times that ugly number, and y is negative 16 divided by that ugly number. And so I can figure out what x and y are. Okay, knowing lambda means now I can figure out what are x and y. And I actually have two values of lambda, right? Because there's a positive one and a negative one. And at one of these values for lambda, let's say the positive one, I'm going to get a negative x coordinate and a negative y coordinate. And that's going to be either my maximum or my minimum. And at the other value, the negative value of lambda, I'll get a positive y coordinate and a positive x coordinate. And those will be the coordinate pair associated with the other one, the maximum or the minimum. I know from geometry that if my original function that I'm trying to optimize is linear in x and y, that means it's a plane in 3D space. And so I've got this slanted kind of plane in 3D space. The domain that I care about is given by this constraint equation, so it's an ellipse. And so I've got an elliptical domain and a plane in space. There's going to be a point that's a maximum, and there's going to be a point that's a minimum. So I really expected to find two stationary points. I'm not going to actually do this, but does everybody see how you could take your calculator? That I don't have a calculator right now, but you could take a calculator, figure out what is lambda, calculate the x value, calculate the y value. You have two different coordinate pairs. And then you could plug in the x and the y from those coordinate pairs into my original f function and tell what the value of the function is. And so the bigger number is going to be your maximum, and the smaller number is going to be your minimum. That's how you could tell. Feel good about that? Okay, so let's do more examples. We don't have a ton of time left. One thing I'll say really quickly is if I'm asked to find the optimum of a function like this, this looks maybe not that bad, but it's a little bit unnecessarily complicated. Because x squared plus y squared is always going to be greater than 0 for real numbers x and y. The square root function is strictly increasing whenever the radicand is a non-negative number. And if a function happens to be strictly increasing or strictly decreasing, that means it is monotone. So if anybody ever tells you the vocabulary word monotone, that's an adjective that describes functions. A monotone function is either strictly increasing or strictly decreasing. And all monotone functions are one-to-one. Meaning the word one-to-one means every input maps to only one output. That makes it a function. But also, what's special about a one-to-one function is that every output value is mapped to by only one input value. And so if my curve is a strictly increasing curve, then every value in the output is mapped to by only one input. And that's important because that means any maximum or minimum of f, any maximum or minimum of the square root of x squared plus y squared is a maximum or minimum, respectively, of x squared plus y squared. If you found a coordinate pair, x and y, that maximizes the square root of x squared plus y squared on a domain, well then, that's the same thing as, I don't remember what I said earlier, but it's the same thing. I don't remember if I said square root or not, but this, maximizing this is the same as maximizing this, and minimizing this is the same as minimizing that. So if you see a monotone function, if you see a strictly increasing or strictly decreasing function of something else in the argument, just ignore the part that's strictly increasing or strictly decreasing, right? And some functions that might be like this are like, if I see that, well, e to the x is strictly increasing. So just optimize x minus 2y instead. Right? Don't go through all the effort of taking, the gradient of e to the x minus 2y when you could just take the gradient of x minus 2y. Way easier. Gives you the same answer in the end. The other thing I'll say is we can have functions of 3 variables and a constraint equation like this one. So in this case, my function I'm trying to maximize is a scalar field that assigns a scalar value to every point in space with x, y, and z coordinates. And my constraint equation is a plane that goes through space. And I say, well, for every point along this plane in space, which point belonging to the plane has the maximum value or minimum value of this scalar field? So we define the Lagrange function to be f plus lambda g. G is going to be x plus y plus z minus 12, because we want that to be equal to 0. And then I take the gradient of the Lagrange function, which is going to be the partial derivatives of the Lagrange function with respect to x, with respect to y, with respect to z, and with respect to lambda. So this time the gradient of the Lagrange function is a 4-dimensional vector. The partial with respect to x is going to be yz plus lambda. The partial with respect to y is going to be xz plus lambda. The partial with respect to z is going to be xy plus lambda. And the partial with respect to lambda is going to be x plus y plus z minus 12. And all of these need to be equal to 0 because I'm trying to find the stationary points of the Lagrange function. So I have a system of 4 equations with 4 unknowns. That is x, y, z, and lambda. So you got to put in some work to be able to solve that system of equations for x, y, z, and lambda. And then if you want to figure out, did I find a minimum? Did I find a maximum? Just take your x, y, z coordinates and plug them back into your original function and try to figure out if that's greater or less than other values of the function. But that's the idea. I'll show you one more example because we only have 8 minutes. So this might be the last one I have to show you today. Find the minimum and maximum of this function. Again, this function is a scalar field. It assigns a scalar value to every point in space with an x, y, and z coordinate. And this time I have constraints plural. I have 2 constraints. X plus 2z equals 6 and x plus y equals 12. So my x, y, and z coordinates have to obey both constraints at the same time. And that means g1 is going to be the function x plus 2z minus 6. g2 is going to be the function x plus y minus 12. And this is how you set up your Lagrange function in this case. I'm going to take my f function, add to it lambda 1 times my g function, add to that lambda 2 times my g2 function, and that's the Lagrange function. The gradient of this Lagrange function is going to be a 5-dimensional vector because I need the partial with respect to x, the partial with respect to y, the partial with respect to z, the partial with respect to lambda 1, and the partial with respect to lambda 2. The partial with respect to x is going to be 2x plus lambda 1 plus lambda 2. The partial with respect to y is going to be 2y plus lambda 2. The partial with respect to z is going to be 2z plus 2 lambda 1. The partial with respect to lambda 1 is going to be x plus 2z minus 6. And the partial with respect to lambda 2 is x plus y minus 12. And to find the stationary points of the Lagrange function, we set this equal to the 0 vector, and that gives us a system of 5 equations and 5 unknown variables. I don't know what x, y, z, lambda 1, or lambda 2 are, but at least I have 5 equations that I can use to solve for x, y, z, lambda 1, and lambda 2. That looks like a linear system of equations, so it shouldn't be that difficult to solve a linear system. And that also means there's only going to be one stationary point of this Lagrange function. And if I go back and I really think about it, the f function is just, it's almost like the distance from the origin, right? But it's squared. The f function is the distance from the origin squared. My constraints, well, the first constraint is a plane, and the second constraint is also a plane. I've got 2 planes as my constraint equations. So to obey both constraints at the same time, my point has to belong to both of those planes. that means my point has to belong to the line of intersection between those two planes. And so I'm basically asking you, for a given line through space, what point along there has the minimum or maximum distance from the origin? Well, you can't have a maximum distance from the origin in three-dimensional space along a line. So the only stationary point we find must be a minimum of f. That's what I mean about like reasoning through your problem to figure out if it's a max or a min. So yeah.
If you did try to do all the work to like try to find a maximum, would it lead you down a wrong path? Like would you get an answer just?
So how would you try to find a maximum? You first start by finding the stationary points of the Lagrange function. There's one stationary point of the Lagrange function. Because we just had a linear system. There's only one solution to a linear system. And so you find that one stationary point of the Lagrange function, and then you ask yourself, okay, I have a stationary point. Is it a maximum or is it a minimum? How do you determine whether it's a maximum or a minimum? If you didn't know from like geometric reasoning, one way you could tell is you could take the xyz coordinates you found at the stationary point and plug them in here and do x squared plus y squared plus z squared. And then take a different point that belongs to both constraint planes, right? Find a different point that meets both of those constraints. Plug that point into the function that you're given and find out which one's bigger, the value of f at your stationary point or the value of f at a different point. What you should find is that the value of f at the stationary point has a smaller value than any other point that belongs to both of those two planes, because that's what it means to be a minimum. And if you find out that's true, then you know it's a minimum. If you find out it's the opposite, if the point you got at your stationary point is larger than another point that satisfies your constraints, then you found a maximum. So find the stationary points first and then try to figure out if the stationary points are maximums or minimums.